our next speaker is Dr. Nibedita Ghosh. She is possibly the youngest doctorate today present in today's session. So she completed and defended her PhD on 14th April this month only, just a week ago. I mean, less than a week ago. From IIT Kharagpur, she did her master's from IIT Kanpur and currently working as a postdoctoral fellow at RWTH Aachen University. I think she is now in India for defense and for our symposium. So thank you. And her research interest includes multi-scale modeling, analysis of numerics of PD, porous media flow, moving interface problem, etc. So I know Nibedita since almost 2 years, I guess. And today she will be talking about domain decomposition of COSMOS model. So over to you, Nibedita.
So firstly, I would like to thanks to the organizer for giving me the opportunity to talk about my research work. So the title of my talk is Domain Decomposition for COSMO Model, and this is a joint work with my postdoc mentors, Professor Arnold Royston and Professor Benjamin Stum. And these are the outlines of my presentation. So firstly, I will talk about the motivation. Secondly, I will talk about the algorithms we are working with. Thirdly, I will talk about spherical harmonics. Fourthly, observation and drawbacks. Finally, some future outlooks and references. So the COSMO model is basically mostly popular in the computational chemistry to compute the electrostatics interaction between a solvent and a solute. But from a mathematical point of view, we can see that these are just the circles which have some overlap. And also the physical phenomena can be represented in the terms of Laplace boundary value problem on a domain which have some number of intersecting balls. So this is basically the link between COSMO and the Laplace boundary value problem. So the reaction potential W satisfies this equation where omega is minus phi on boundary of omega, where this phi is just the free space potential generated by the solute's charge distribution, and omega is the solute's cavity consisting of a union of possibly van der Waals ball omega I, each have center xi and radius ri. So what we do in Schwarz domain decomposition is basically, firstly, we will decompose the whole complex domain in some simple subdomains, and we will solve our PD in each of the subdomains, and finally, we will combine all the local solutions to approximate the global solution. That is the basic idea between Schwarz domain decomposition. So we already have some results in our hands, so which says that if our domain omega is the union of balls omega I, then if our boundary function is taken from the space C boundary omega, and if we consider the classical Laplace problem, del W equals to 0 in omega and omega is equal to phi in boundary omega, then if our boundary function is taken from the space H half boundary omega, then the classical solution of this Laplace system will also be weak solution for this Poisson system, where this U is nothing but W minus phi E, and phi E is the H1 extension of phi, and this nonlinear term F is nothing but minus of del of this phi E. And this is the algorithm of Schwarz domain decomposition. So for initially we are starting with the two circles because there are, in reality definitely there are so many circles, but we are starting with the two because we will then increase the number of the balls. So we are considering domain like the first figure where we have some overlaps. We are not considering this case where two balls are intersecting at certain point. So this is the idea of natural domain decomposition. Firstly, we will choose the initial function W0, and then we will run our K, and this globally function will be taken as W0. And this is the solution of this system. So basically the idea is firstly we will solve on omega 1, and when we will solve for omega 2, we already have known for some boundary values which are included in omega 1. So for that point, we will take the value from the previous iteration that is defined as Wi minus 1 globe. And that is why we will update our solution at each step, and finally we will get our final solution. So that is basic idea of this natural Schwarz domain decomposition. But this technique is better suited for the numerical simulation, but we are also interested about to see the efficiency and accuracy of the method. And for that, basically we are using this homogenization domain decomposition algorithm, where the idea is almost the same, only we are working with the error function. This EI, this is going to H10 omega I, because we are defining here our U0 such that it will be 0 on the boundary. That is why it will go to H10 omega. And this EI is the unique solution of this Poisson system, where this extension EI is defined by 0 outside of omega I. And this ui is just defined as the error function. Ui is nothing but ui minus 1 plus ui. And this is the idea of correction dd. But we already have the result that these two algorithms are basically equivalent. And we will employ our correction dd for the analysis purpose and natural domain decomposition for our numerical implementation. So already there is result where the subspace problem are solved, assume that they are solved exactly, not approximately. And for the exact ddCOSMO, there is already result which says that the Schwarz domain decomposition algorithm is linear iterative. But this is for the exact case. Our analysis is about the inexact case. And this also a result which is about the exact. And this proof is very technical where they says that this H10 omega I, where we have m number of balls, this is closed in the whole domain. And if we write our E as the error propagation operator as the product of this, where each of Pi is the projection operator of omega on omega I, then we will have this norm, which is nothing but H0 by 1 plus H0. And this H0 is the stability constant. At this point, I can't just explain that because it is a very complicated form. But if you're interested about the proof, you just can have a look in this paper where they have this proof. But few remarks on these results, we can see that this is always less than 1. So this method is always convergent. Secondly, lower values of H0 will give the faster convergence. And this H0 just depends on the amount of overlap of the balls, but it does not depend on the number of balls. That is the great advantage we have. And also it depends on something called exterior fatness of the domain. And these details about the exterior fatness of the domain can be seen in the paper, because here basically they are taking a point outside of the domain and some calculation is done. And there are also some results on the stability constant for the exact ddCOSMO, which says that the stability constant is 0 of the algorithm. And if there is the number of interior balls, where the interior balls is defined in this way, that we will take those components of I. For those, our boundary intersection will be 5. Then this H0 will be less than equals to some constant C3, which will depend on the local geometric properties of the domain omega. But definitely it is independent of M. And if it is not equals to 5, then there will be another constant C4 and df square. This C4 also depend on local geometric properties. And basically df is quantify the global exterior fatness, which I said before in the before slide. And now comes to our objective. So we will solve the Laplace boundary value problem, which I already shows in the previous algorithm. This one by numerical techniques. And we will approximate the solution by using spherical harmonics. And then we will employ numerical quadrature to compute the coefficients of the series expansion of the solution. And then we will study the behavior of the inexact solution for different number of iterations and different choice of degrees of spherical harmonics. And lastly, we will study the accuracy of the numerical approximation. Although we are just on the way of the objectives, we did not fulfill all objectives yet. So firstly, we will talk about the 2D Laplace system. So in our 2D Laplace system, if we consider a ball with radius 1 and center at 0, this is just the function and its polar form looks like this. And its solution is just computed by the separation of variables. It has explicit form 2, where each of the coefficient a0, an, and bn can be computed in the integral form 3. So if we want to solve this numerically, there will be two errors, where first error comes when we approximate 2 by a finite number of terms, and 3 when we compute these coefficients by using some numerical quadrature. Similarly, for the 3D case, this is our Laplace system, and the polar form is again given by this function. And now the solution is explicitly in the form of 4, where each of the coefficients ALN, and this is basically the Legendre polynomial of order L. And this is a function e to the power im5. And now we will define our spherical harmonics. So if we choose our L from n0, that is the natural number, and including 0, and our mod of m is less than equals to n, and for this choice, our spherical harmonics is defined in this fashion. So basically, you can see that the right-hand side have the form of 4. So you can write our solution in terms of the spherical harmonics, where theta phi is just like in the spherical thing, 0 pi and 0 to pi. And we need some of the properties of this. And its first property says that this spherical harmonics is the eigenfunction of this operator corresponding to the eigenvalue L into L plus 1. And this operator is nothing but the angular part of the Laplace operator in spherical coordinates. That is the advantage. And the second part is that spherical harmonics is L2 orthogonal. And lastly, they will form a complete orthonormal set of Hilbert space. In the L2, this is boundary of the ball. these properties we need. So secondly, there is something which called as if of this boundary function, and this s theta is just the boundary of the sphere, and it is L2 square integrable. Then we can write our f in terms of this form, where ALM is the coefficient given by this integral form, and this YLM, this is the spherical harmonics, and definitely they will converge to the function f in L2 S2. And spherical harmonic space we need also, and that says that if we choose our D, that is the dimension of the domain, from a natural number n, and if our small n is taken from n0, and then for the component x1, x2, xn, we define x power alpha as this one, and this is the space of homogeneous polynomial of degree n in D dimension, which says that this is the polynomial and this is the homogeneous polynomial. So this alpha is n, and each of the coefficient can be also in C. And this yn Rn is just the polynomials taken from this space, which will be satisfying this Laplace operator. Laplace of P will be 0. And finally, spherical harmonic space, that is the restriction of this space on the surface of the sphere. So that is one dimensionless. And nextly, we will write our boundary function in terms of the spherical harmonics. And for that, we need this orthogonal decomposition, which says that this L2 SD minus 1 is nothing but the orthogonal decomposition of y and d, which we defined in the previous slide. And then for f goes to L2 SD minus 1, we can write our f in the unique decomposition form, where each of fn is n spherical harmonic component of f. And we can write our f psi, if this orthogonal basis is already known, then we can write in this form, in the series expansion form. So now we will come to our system. So basically, firstly, we are solving in 2D case, but here we draw for D, but we will study for D equals to 2 and 3 first. And then we just for numerical simulation, we can do up to 3. So our system is del equals to 0 in D-dimensional ball, but D is 2 or 3 our case, and U is F. And now we can write our F in this form, where Y is just spherical harmonics. So the numerical aspects is just first we will error is come because we will approximate our 6 by some finite number of term n, and secondly that each of the coefficient has this numerical expression. So to compute each of the coefficient we need some numerical quadrature. So error also comes into the picture. And we also find out the result which says that approximate error, that if R is an integer and if our f is L2 S2, which is R times continuously differentiable over S2, such that all of its derivative goes to L2 S2, then there exists a constant C which will depends on R, such that this f minus fn is just a truncated version of f, where which considered up to n number of terms is less than equals to C divided by n plus 1 into R. So we now make some numerical results to verify this. So we consider the discontinuous function f0 and also consider the function C infinity. And we observe these results in 2D. So the absolute error in the left-hand side is plotted for f0, and in the right-hand side it is plotted for f infinity, and this is the squared error. So you can see that error is decreasing for the differentiability of the increasing differentiability of the boundary function f. So if our f is smooth enough, then the error will decrease. And nextly, we compute also the error for the solution. So if our domain is BR0 and if f is L2 boundary of omega, then if we consider this is the exact Laplace system and its solution is written by U star. And for n greater than equals to 0, we are considering our discretized Laplace problem, which is nothing but where we truncated our f up to n number of terms. So U is fn on the del boundary omega with the solution is un star, where this fn is the n terms truncated Laplace series, and these two are the solution of these two systems, and then their error can be approximated by this term, where r is the radius of the ball, and there is a factor 2n plus 4, and this term is we already computed. So if f is r times continuously differentiable, for that we already know that this L2 boundary norm can be defined by some estimate which we stored in this slide, and we just use that here, and that can be have in this form. And this verification also done in a master's thesis that says that this is the plot for f0 and this is the plot for f infinity. And here we can see the verifications of these results, that plots of the absolute error and compared with the f minus fn. And the left hand side here we have the factor 1 by 2n plus 4, and the right hand side also says the result same. And now the observations and drawbacks we observed in the numerical simulation. So firstly, if we try to solve the thing in 3D, then the Lebesgue quadrature is more efficient compared to the trapezoidal rule. Secondly, but the drawback is that the Lebesgue quadrature can be used up to n equals to 65. That is, we can truncate up to 65 number of terms. We can't consider more than that. But 65 is also very big for our calculation. And we also have a problem in our analysis, like from analysis point of view or mathematical point of view, that is basically the intersection point of two circles. At that point, we will have a discontinuity. And we also show that if we increase our number of n, then this discontinuity will be decreased. That is, the discontinuity at the intersection point will be number of polynomials. And there is also an observation which says that if we want to reduce our computational cost, because the main drawback of this method is that it is not computationally efficient, and the time using by the low value of n, like we can take a finite number of n, and the final step we can use some extra iteration like the m. That is what it is shown that if we extra iterate like 1 or 3, then our error behaves like that. This is the n maximum, and here error is plotted for the choice of n 1, 2, 3, and 4. And then we also have that the error behavior is not influenced too much by the domain geometry. That is, overlapping size does not affecting that much to the impact of the convergence of the method. That is the observation we made by numerically. But all these numerical observations are just made in 2D. So, and convergence becomes slow due to the non-smoothness at the just two isolated points of the boundary condition. So basically, we have 2 points, the intersection of 2 circles, and at that points there have discontinuity, and for that, basically our convergence process is becoming slow. And nextly, if we talk about our future outlook, so in 3D we interested to study about the behavior of the solution, because in 3D we did not able to do so much still now. And the shape of the in 3D, their intersection point definitely will be have a form of arc, and that will be really difficult for numerical point of view. And for large number of n, we are also interested to see the numerical approximation, because we do not consider large number of n yet. And error analysis of for the discretized problem is our main goal of the calculation. And these are the reference. Thank you.
Thank you, Nibedita. So C has finished well in advance for a lot of scope for questioning. So anyone have any question, feel free to ask, unmute and ask questions to her. Maybe I'll start with a question. So,
Yeah.
Nibedita, you mentioned that so can you go back to your problem formula, like the example problem that you were trying to solve?
Yeah. Yes.
Yeah. So basically, you are solving a Laplace equation, right?
Yes.
Laplace problem. So you are trying to give a different kind of numerical scheme for solving this problem, right? That's what you are trying to do. So the basic question that comes to my mind is why we are looking for some new numerical schemes when there are existing ones.
So the basic idea is firstly that it is purely convergent. We don't have to worry about the convergence.
Okay.
And the second thing is that the convergence does not depend on the number of balls, like, because in the realistic situation in the computational chemistry there are so many large number of balls, like there are some 1,000 or something like that, and our analysis does not depend on the number of balls. But for other scheme we can't say about like that, like we can't remark like that in finite element or finite difference, this kind of techniques.
Okay. And so yeah, so what I was thinking, so you started with these basically chemistry motivation, which is the main driving force behind your COSMO model. So you are taking these balls really spherical, or it can take any shape eventually.
No, it's spherical. For this moment, it is for spherical.
So you are only restricted to take spheres in 3D and circles in 2D. I mean plates basically. So you can't take elliptical regions, and why not?
Because we are approximated by spherical harmonics.
Yes, but you can always have ellipse also as a perturbation to spherical harmonics, isn't it?
But this one is also numerically like very difficult because it is slow. But we are working on that because the process is very slow for 2D as well. And for 3D, we just don't know. But that is for the simple figure like circle. But
Okay.
if we consider some kind of elliptic or something, I think this will be more time consuming thing. Like, but I am not also sure at this moment.
Okay, and this boundary condition here, as I can see, you have taken a Dirichlet condition. So
Yes.
can I take other type of boundary conditions, like other boundary value problem? I
Yes,
keep the same
boundary
problem.
condition can be changed. Yeah, boundary condition can be changed.
So
That
can I
is not a
take
problem.
part of the boundary to be Dirichlet and part to be Neumann? Is it possible
Yeah,
to work?
that can be taken. Yeah, that can be taken.
That can work. Okay, thank you. So anyone else want to ask questions to Nibedita?
Okay, hi. So maybe I can ask a question. Thanks for your talk. I didn't quite understand. So if you go back to your first or second slide, you had like a domain where you had various overlapping spherical balls. So ultimately, yeah. So this, or even you had one more. I think maybe I.
No,
Anyway,
picture
so okay. So is your solution then on this domain, or is it like on a single sphere?
No, initially we started with 2 circles.
Okay.
Because it is real in realistic, definitely they have more number of balls, but we started with 2 number of balls because the convergence does not depend on the number of balls. So if we can achieve our thing for 2 or 3, like, because we are considering in this theory we show for m number of balls the results, and the convergence for the theoretical part, the analysis part does not depend on the number of balls, like does not depend of m.
Okay. So in that case, okay. So but okay. So your solutions are valid for 2 circles.
Yeah, initially we started with 2. Yeah.
And they are overlapping, right?
Yes, they have overlapping.
Okay, so but then but you said that because you're using spherical harmonics, you won't be able to apply it to an ellipse. I didn't quite get how you're able to apply it to like.
Okay, so basically
like
we are
this.
solving this Laplace system, this Laplace system. So, and we are considering it for 2D or 3D case. So if, for example, we consider it in the 3D, like this is our solution 4, right?
Okay.
Explicit form, and it can be written in the terms of spherical harmonics because spherical harmonics also have the same form.
Okay.
So we are basically approximate our solution by the spherical harmonics. We are not able to solve it exactly. Here we are implementing basically the spherical harmonics.
Okay. Thank you.
Because our right hand side is ln into r power l into nothing but some constant into this PML at theta phi.
Okay, thank you.
Yeah, okay.
Yeah, any other questions from the audience? If not, then let's thanks Nibedita once again for this talk, and
Thank you.
yes.